Hey everyone, welcome back to Cracking the GRE Math Subject Test, Calculus 2. We are on question number 14. And I would say this question is pretty tricky because you're asked to find the mixed derivative of f at the point 0, 0. And you'd be tempted to go ahead and differentiate this expression with respect to x and then differentiate it again with respect to y. But for one thing, you're going to waste time because it's kind of complicated and requires a lot of simplifying, and then eventually when you do find out what the expression is for fxy, then when you plug in 0, you just get 0 over 0, so it's not really going to help you. The way to do this problem is to work backwards. First of all, write the definition for fxy at 0, 0. So remember that this means that you're taking the derivative, the partial derivative of fx, assuming you know what fx is, with respect to y, and evaluating that at 0, 0. And the definition of the partial derivative of fx with respect to y is the limit as k goes to 0 of the partial derivative of f with respect to x at 0, 0 plus k, which is just k, minus the partial derivative of f with respect to x at 0, 0, all divided by k. Now, in order to evaluate this limit, we're going to need to figure out what f of the partial derivative of f with respect to x at 0k is, and what the partial derivative of f with respect to x at 0, 0 is. So let's start with fx. Here you can actually differentiate f with respect to x at 0k. You can actually differentiate this expression. So let's evaluate. Let's rewrite this as x cubed y minus xy cubed all over x squared plus y squared. Okay, so now if we differentiate this with respect to x, we'll use the quotient rule. That's low x squared plus y squared, d high, that's going to be, remember, with respect to x, so we'll get 3x squared y minus y cubed minus high, that's x cubed y minus xy cubed. D low is going to be just 2x. Square the denominator, and away we go. Alright, now let's plug in 0 for x and k for y. 0 for x is going to just get rid of this whole term. That's going to be 0. Here we're going to end up with k squared times, this is going to be 0, so we'll have negative k cubed divided by, this is going to be 0, and we'll have k squared squared, so that's k to the 4th. Well, at every point except 0, this whole thing is going to be k squared times k cubed, that's negative k to the 5th, divided by k to the 4th. We can cancel out k to the 4th, and we'll get negative k. Okay, so this part here is negative k. Now we want the partial derivative of f with respect to x at 0, 0. Here, if we just plug in 0, 0 into this expression that we found, we're just going to get 0 over 0. That's not going to help us. So we will use this definition again, the definition of the limit, to write that fx at 0, 0 is equal to the limit, let's use h goes to 0, of f at h 0 minus f at 0, 0 divided by h. Okay, well, what is f of h comma 0? Well, if we plug in 0 for y, that just gives us 0. And f of 0, 0, we know that's also 0 over h. And we're taking the limit as h goes to 0. Well, this expression is always going to be 0. So this numerator is always 0. So the limit of, and so for every h not equal to 0, this whole fraction is going to be 0, which means that the limit as h goes to 0 is 0. Okay, so this part here we found to be 0. So now I think we're ready to evaluate this expression. This is going to be the limit as k goes to 0 of negative k over k, which is just, this is always going to be negative 1 when k is not equal to 0, so the limit as k goes to 0 is negative 1, which is answer A.